This talk is called Stop, Get Some Help, Design Your Implants Properly. Before we jump into anything technical, just an introduction into who I am. My name is Brandon McGrath. I am on the red team at OpSec. It's my 4th year speaking in a row at SteelCon. And any ramblings about most stuff today and anything else will be on over those 2 blogs just there. So today's today's goal is to look at kind of the state of malware and telemetry detections and try and understand how they kind of work and how we can have implants operate within those boundaries. Kind of discuss some of the detection gaps and how we can kind of work within those, and then overall just try and take out all the guesswork from payloads. And I'm sorry if the developer for this tool isn't. No, sorry, if it was IT guys. He's in the room. So, whilst there are some really cool stuff in these kind of public loaders you see on GitHub, where they're full of, all this fun stuff, if anything goes wrong with any of this, it's detected once by a client, it ends up on VT. This is banned, essentially, right? You're going to have to rewrite this from scratch, and you're going to enter this error-driven approach of it's detected, what detected it, and kind of keep going that way. And if you're not in a kind of privileged position where you have dedicated people to kind of work on this stuff, it's a big time spent. So if you do something like this, and you build it and you put it on VT, it's kind of dead, and you're back in the R&D cycle now. So the idea here is to kind of prevent people from building these monolith loaders, as well as having defenders write real laser signatures that match this particular thing, but not the underlying mechanisms. Is this okay?
It works for you.
Would it be a lot of debugging to fix it, or is it just best to keep going?
It's your laptop and the box is not schematic wide. I don't know how this will be.
I'll just commit to it then. Okay. I'll turn my laptop around because it's not to show. So, what we're going to do first is we're going to talk about kind of the state of payloads in 2026, that says, and we're going to look about how the progression has changed over the past few years, and it's quite drastic. So, in about 2020, this was kind of like, how's getting this cut off there. In about 2020 and 2021, it's like the golden age of EDR agents. This is when I think a lot of the industry realized game hackers were doing really well in terms of circumventing anti-cheats and things like that. So in about 2020, that link down there is from a colleague, when was it, MDSec, where they were first figuring out how to break AMS and ETW by kind of memory patching and things like that. And then around that time, it kicked off this huge spiral of people just ripping into EDRs, antivirus, and that kind of stuff. I mean, we had a lot of things come out of it. So at the time, it was like syscalls, syswhispers, the 23 different Hellsgate variants, all that kind of stuff. And it worked for a really long time. It's, from our perspective, it's hard to say why it worked for so long, but I guess people didn't really expect it to kind of use, Windows and in that kind of way. So there was no real detections, and it worked for a very long time. Around the time, there was some ways to do it through like kind of CPU registers and that kind of stuff, but it worked for a great time. AMSI was huge at this point. I don't think I've ever seen or cared for AMSI the past 3 or 4 years. So that was huge, that thing I did at the time. But the main thing that people were doing in this era was just heavy obfuscation. So things that were, there was like a PowerShell thing that invoked something or other. And it was just garble the life out of everything and anything. So it was heavy obfuscation in .NET was quite common at this time. And that we had there was one time Michael and I had a deserialization vulnerability on a client, and where we obfuscated the payload for PowerShell, which was changed to James Acaster references, and that kind of put a signature on that. So obfuscation was king at point as syscalls. You kind of jump forward to now, and it's completely changed. So EDR vendors have caught up with most of these primitives. ETW and AMSI patching that worked, was used for years, is now an IOC. Remember, integrity checks are going to see that the return values have changed and things like that. People moved on to kind of hardware breakpoints to kind of handle that. But now you have kind of the debug registers that are attached to the threads now, stuff like that. So there was this constant evolution. So syscalls, that's statically an IOC now. They're detectable, just turn on the variant statically. They're also detected on use lands and kernel lands as well. Some of these things, again, when I talk about this stuff, I'm not saying IOC in terms of like globally, EDR vendors are going to handle this completely differently. But when I say it's detected, I'm referring to the CrowdStrikes, the SentinelOnes, and kind of NDEs. But now, as well, ML has came a really long way in terms of seeing some of this stuff. So as I spoke about kind of the intricacies and things that are working within ML. I'm not going to talk about it today because it is a huge topic. And there's two other important things that's happened as well. The second to last point being kind of the most important things, in that a lot of the open source research that was pioneering this early EDR stuff back in 2021 is now completely stopped because EDRs eat it up just as quick as the other red teams do. So teams tend to keep this stuff really close to the chest now. But a lot of the current focus has been on core stacks. And if you Google core stacks, you'll see kind of all this research. It's really cool stuff. It's never, for me, inherently been something I've kind of cared about. It's never been a detection point for me. I've never had a client talk about how their team were able to discover this kind of stuff, but it's cool stuff. So over 2020 and 2026, it's gone from shoving all these all these bypasses and evasions and breaking telemetry, obfuscation, to now having to pick what you want to use per client, per EDR, per every other application control. So I'm not going to talk about static at all today. That might come up once or twice, but it's not the point of this. So I've got one slide, and it's just this. When kind of at the end of this talk, and I've kind of spoke about everything I'm going to talk about, you've got to just remember statically as well, when that file touches disk, you're still getting hit with it. You're still going to get the ML predictions. And I'll kind of ignore Kappa a little bit. That's kind of for you guys to, when you're looking at payloads, to see what kind of signatures capabilities the binary has. It's not a detection vector. It's just an indicator of, capability, essentially. Hence the name, I guess. Yara is interesting. We've seen a lot of EDRs have a really small high fidelity list of Yaras they kind of use. And, they won't just get fired on disk, right? You'll see them come from kernel to user space, and they'll hit kind of like the write, when a memory gets written, you'll see the Yara will run over that new allocated and written memory. But again, I'm not talking about any more with static today. Just to ease us into what I want to be talking about, there's two, asterisks that matter sections of this. The first one being the security products that matter. So when we're working with payloads of any variety, whether it's XE, DLL, reg file, VSTO, macro HTA, whatever it is, we're going to be working in the boundaries of different products. And there are four, cut you off, but there are four that I kind of pulled out as being the ones to kind of think about. There's about 20 other different types of security products here, but these are the four that kind of hit on what we're talking about. EDR, application control, PAMs, and then DNS web protection. So each one of these creates some sort of obstacle we have to consider and work around. With EDR, we're going to look deeper into EDR in a second, but most of this is going to be, if you think of EDR as just gather telemetry, run rules later, it's going to do a lot of that stuff, but skip that for now because it's going to come shortly. Application control, something like threat locker. If you have the combination of MDE, CrowdStrike, something like that, and then threat locker, it's going to be a bit of a ball ache to work on that machine. The application controls kind of limit what software is allowed to be on that box, what can run. So if you bring in your own interpreter, but that interpreter is kind of blocked the app control, it ain't going to fire. That kind of stuff. But again, I'm not going to go into too much detail here. PAM's a little bit of a diagonal one. You can't predict it or really plan to work around it, just kind of how the access to that particular user or box is going to go. Worth remembering that it exists. But then the other one that's quite important is the DNS web protection. So we have a tool at CS called Specular that Oddvar released, I think it was 2 years ago. It is an Outlook front page attack. There's a specific detection there for CloudFront coming out of Outlook, right? So there are rules that can hit at this scale. And also in this area, it's a little bit off to the side, and it's kind of like on the Cisco umbrella side of things. Sorry, the network level stuff. I had an engagement where the client spun up a new laptop, plugged it in next to his desk, and then I ran an implant on it and worked from there. But because it was a brand new laptop, across the 30 days I was on that machine, the amount of HTTP outbound went up like 2,000,000% or some ridiculous number. So you've got to also account for the amount of HTTP that goes out, or protocol, DNS, whatever. You got to account for that as well. If you wanted to visualize that, you kind of look at it in this kind of way. So it's kind of a lot to think about. We try to abstract out as much as they can to the top level where possible. It kind of looks like this. You have the target environment, which will go down to kind of what controls exist, the EDR, application control, network protections, that kind of thing. And they're going to funnel down to kind of the telemetry that's going to be involved. Anything that's going to get in your way. So blocking execution, elevation, and kind of comms in that regard. EDR is going to be the main one for us though. You can work with it if you don't kind of keep notes on what works and what doesn't work. Not any of these, but specifically EDR and the different variants of EDR. I recommend you do. You know, what worked, what didn't work. If you're in a position with a client where they're happy to share information with you, see if they can tell you specifically what happened. Sometimes in their view, they'll have far more information than you'll get. So that says none has anything to do with endpoint hardening. So this takes into no consideration to any GPOs in place, any of the build review findings you've actually put into place. None of that matter. I'm not talking about any of that because you can't account for it. You can assume it is up to scratch with kind of requirements, but again, we can't predict any of this. So the EDR mechanisms that matter. There is a ton of these. So for those who aren't familiar with what an EDR is, I would define it as a system of telemetry sources on a host that have the ability to detect and respond to malicious activity. The main difference here from EDR to AV would just be AV is just static signature of a mini filter. Is this thing known? Bad. Boom, step. EDR is going to have a ton more access, which we'll see in something like this. This isn't everything. I'm sure if you look through patents and things like that, you'll see other telemetry sources here. But kernel callbacks, DLL hooks, ANSI, call stacks, minifers, ETW, machine learning, DLL notifications, the Windows filtering platforms, that's the wrong way around, the mark of the web in orange. It's mark of the web just off to the side there in orange, which is, it's in orange because it's not, I wouldn't say it's a detection boundary, a prevention boundary, but it is worth considering. But yeah, it kind of looks like this. And if you were to abstract that out even further into not the specific terms, you get something that looks like this. That is awful from your perspective. But that's how we have process, thread, registry, network, and memory telemetry. So that's going to be any way the kernel can have a callback for a new process started, new thread started, new registry read. Network, you might look into kind of ETW side of things. Memory telemetry can come from ETW as well. So allocations and things of that nature. Event logs and application logs, kind of Windows event IDs and anything applications are willing to censor over there. Threat intel, bottom left. So hopefully it doesn't hit, unless you're doing adversary simulation. I wouldn't expect that one to kind of matter to you. Then script and telemetry, similar one to the one above. That's kind of your AMSIs, that kind of rubbish. And then bottom one down here is sandboxing, because once you've considered all of this stuff, they can also just send it off to the cloud and run it, right? So no matter how much you do here, you might end up hitting the sandbox. But quite often with EDRs, it's expensive to just do a sandbox, right? So unless the score is in the suspicious range, it won't fire up. See, if you kind of build and plan these files properly, you shouldn't ever really have to deal with sandbox. There are an insane amount of telemetry sources. As I say, if you look up the patents for some of these, you'll probably find even more that aren't there. I probably missed some obvious ones that you guys are screaming in your heads at me, but they're the core ones I could think of. However, only a finite amount of those are actually high fidelity. The rest can just be considered kind of like enrichment. So process start, thread start, that kind of stuff. Really useful. But the fact that some random process called out to some random website is interesting. And if you can tie that back to a PID that has, that eventually was involved in some sort of incident, then it's enrichment, right? Like you're clear in that perspective. But being aware of them is important for your kind of triage. We have these two preamp blogs here, we spoke about and built out kind of programmatically how the data output would be for a kernel callback for a process start. We built out the kernel, we got that to use land, we print out the JSON, and that'll kind of be in there. And I also did a talk, my first talk here actually, 4 years ago, was entirely on the subject of rebuilding ADR components and parsing out their data to get to userland, so we can kind of see from a red team perspective all of the data that we produce when we just literally double click file. So that is all of the prerequisite information. Now we're kind of jump into the actual meat and potatoes of it. So what we're going to do is we're going to create this scenario that says we are on an assumed breach and have access over RDP to a VDI. To bring our tool into the environment, we want to deploy C2. This does not handle the caveat of if you are an assumed breach, day one is access to a VDI over RDP. Maybe don't try and run an implant day one, like burn the entire operation. But we're working within this boundary. So the first step, maybe even step 0, is kind of figuring out what kind of execution primitive you want. And we're going to get really granular with the entire loader here. So we're going to start at the abstract level is what is it? So there are a few options. And the things we need to consider. So we need to consider what security controls get involved, what telemetry is generated, what assumptions you need to make about the host, and what when we pick one of these payloads, does it push us down a certain way? Using the public specular as an example, that requires Outlook. It requires a GPO to be not set to have the patch in it. It limits us to VB script in a push-based manner. It's not as linear, so it kind of limits us down a certain way. However, if we want to just copy over an exe, we have all the ability of, C and Win API in a very nice, convenient way. But then we have the fact that we've copied an exe over, right? So that's going to be another thing. So every time you pick any of these, there's spiders out into all these different things. If you were to package a known good application in a zip and it had a sideload vulnerability, for example, double click the sign binary, bada boom, loads a sideload of a DLL. That could be one. But then you have the fact that you bought in a zip or you bought in an ISO. So I would try, my main thing here is to try and convince people to start relying on one mechanism and just think about how what you're bringing in to package whatever you want to package, how that's going to spread out into more telemetry. But for us, in this talk, we're going to just focus on XC over IDP, just because it's easier to talk about. And when I say like a good loader or a good primitive, this is kind of how I define that. It's something that isn't in a public rule set like Elastic. If you look at the rules for those, they detect all sorts of cool stuff. It has no prior research of logs, which is probably the hardest thing on this list to do. It takes a lot of time and a lot of energy and a lot of mental output for this. The primitive goes through some benign channel would be a really nice thing to consider. And that's like a sign binary, doesn't have a typical loading logic, is a fun one. And the execution tree is weird. So what I mean by that is, if you opened up CMD, you did a // on your exe, and now you've got, CMD, malicious file.exe, that kind of stuff. Kind of avoid that. So if you can have something that, like the sideload's a great one. If you package a sideload, you click on the sign binary from, some third party. That goes through the sideload process, and then you get kind of like clean explorer up to third party. So, something to consider. I wouldn't consider these hard rules, just kind of micro process for that. So the usual suspects, and we see it in all of the malware how-to guides. Ignore my non-C comments in that, I realized today. This is what they'll show you. They'll show you int main, LP void, virtual alloc, then you get your mem copies, virtual protects, you create threads, and your websing logic. You'll see this everywhere. It has inherent problems. Int main, for example, that's going to pop up in a console for you. So that really should be a win main with the system subsystem rather than console, I believe it is, or Windows, I forget specifically. Mem copy, that's just a straight buffer to buffer copy. That's just MSCVRT or MSVCRT, I forget which one it is. That's just a straight up copy. Virtual protect is interesting. So back in that 2020 period, it was just allocate, write the memory to read, write, executable, and then carry on with step 3 and 4. However, the fact that RWX memory exists is now an IOC. I've never personally heard of anyone being detected for it, but it is in all the guides of how to detect malware. So kind of take that with a grain of salt as well. But nowadays, it's best to do the virtual alloc with kind of rewrite and then change it kind of throughout. Create thread and then wait for single objects are quite literally going to just create a thread and then wait for single objects, going to just wait on that handle until it kind of finishes running. But in our case, it should be never. And there are a lot of issues here. So with create thread, if you do it just straight off the ADDR, your call stack is going to be full of private memory ranges, for example. If anyone looks at that, it's just going to look, it's going to look like malware. It's going to feel like malware. Probably going to smell like malware. And it's a pretty good, it's a pretty good indicator. This is where a lot of that kind of call stack work comes into play. And it's harder to do if you don't control the C2. I think Cobalt Strike, for example, are heading that way now. They do have the sleep mask and stuff, but we're going to talk more about this a little bit as we go further in. I've spoken about memory regions and thread IOCs and kind of the detection mechanisms for those kind of extensively in these two trust set blogs. It's cut off most of it. Windows processes, always nefarious anomalies and that's what it's called. Memory regions and threads. So if you want more detail on those, that specific stuff, that's in there. Okay, so what we're going to do now is prep the loader. So we've decided on an exit. We've ruled out we don't want a HTA, we don't want a whatever, we don't want a VSTO or MSI, whatever. We're going for an exit. That's what we're working on. So the very first step, that's annoying. The very first step is kind of target validation. So if you think of this guy, what we're going to do now is essentially empty this out when we look at this. So imagine this is empty, just int main. So the very first actions I'd recommend are mutex is optional. So the mutex is going to kind of just let you know if this mutex already exists, and we can use it as a way just to say, have we ran here before? You might not want that. You might want to be able to run multiple in the same instance. That's kind of, if you want multiple, you might be looking at kind of like relaying and things like that. But that's an optional one. The other one is keying, and I think for us as people that are doing red teaming and this kind of stuff, we really probably should be keying for the sake of client scope and just for the sake of kind of blue teams getting in your way and being annoying. So I'd recommend that. There's a ton of options for keying mechanisms you can do it. And the same for mutex. I think there's a few other ways you can kind of do, have I ran here before? There's a few ways to answer those questions. But keying, I've actually got a blog on that as well. It's just on there. But no one likes unintentional exposure. And then if we match that criteria, we can kind of continue on, right? That's the idea. Or we bail right away. The next thing, once we've decided on that this is the environment for us, we're happy with it, it's meta keying, we've decided if we ran here or not, we can go to prepping the runtime. A thing a lot of people tend to jump to with these public loaders, these monolithic loaders, is everything is resolved all the time, ever. So I don't know if you've ever spoken to someone that does malware reverse engineering, or you've seen streams from OA labs. They always say they can tell when it's a red team implant. And it's usually because it is crammed with everything from, the first quarter of May's research, 2026's research. So my advice here for all three of these is to not do them all the time. When we're talking about the ML stuff at ZeveCon, one of the main things there that brought ML score all the way down was having imports, right? So 0 imports is a really bizarre file that makes no sense for it to be on Windows. That's absurd. So the idea is my suggestion, my personal suggestion would be to import a bunch of stuff, maybe have some dead functions that run, don't do anything, but they import more bunch of scalability. You can fudge it with macros and stuff like that, which I showed in that talk. And then the things that you want to use, so your loading mechanism, components, whatever they are, they're the ones that are resolved. So you get kind of a blend. So it doesn't look weird. It has some stuff. If you use Python libraries like Leaf or PE file, I think on a PE file, Leaf definitely does it. You can just add arbitrary data to the PE. So one thing you can do is pull it out of MS Paint, for example, and just re-import it into your binary. You do have to be careful though that you don't call one of those, because Windows isn't going to reload it for you. So you have to import them, then at runtime, actually clear them and reload But there are three categories here. There's API resolution. There are 3 ways to do it. There's probably more than 3, but there's 3 main ones that you'll see. Just straight up importing it, just as is. You can use the get proc address kind of approach, or you can kind of do the export parsing. The first one isn't really an IOC. If you look at the kind of the ML side, it gets really weird about some imports, but not others. So that one we can't really, I don't know, I wouldn't suggest kind of messing too much on. But get proc address, and the export parsing mechanisms, and there's probably a few others, they will introduce some sort of, definitely some sort of, if a person here looks at it and they see get proc address, they'll be going straight for the cross references to that. Export parsing is bad and detectable just statically through Yara and balls like that. So whichever way you decide to go about this, you are introducing some sort of potential issue. The rest of that, why it matters for that one, says static footprints and runtime visibility. For that category says module loading. This is kind of the way you want to import or load in, ADB API 32, for example. You want to get some functions out of there. How do you do it? Do you just import the functions you need, like the one above, or do you do like load library get proc address combination? You can do a proxy kind of approach where you use RTL register wait, which kind of clears the call stack for it as well, which is quite nice. That's kind of the way I like to do it. And then I forget what existing modules actually is. I can't remember what that is. And then the import is what I spoke about earlier, which is the import some others. So if you cleaned that up so far, if you look a bit something like this, you'd have your kind of win main entry point, and you'd have your, if keying's bad, bail. If it's already running, bail. That's kind of where we're at. So at that point, we've still written nothing to do with the loader. It's still just prepping kind of, is the environment correct? Is the file going to work where you want it to? So hosting the telemetry, this is extremely optional and probably the most, other than loading, one of the more aggressive things you can do. A lot of IOCs will come out of this. Some ADRs do it more than others. So if you look at something like Sentinel-1, they load their, what do they call it? They import a fake entry to the PEP for like NTDLL with like the 1 for the L, for example, which hits page guard if you kind of hit it and stuff like that. They do really aggressive userland hooks, for example. CrowdStrike did it as well. You won't see it with MDE, they're ETW based. So knowing kind of that, kind of profile EDRs as you go, if you have the ability to kind of update them, which is really hard to do, kind of keep up where they're going. But for the most part, an EDR now is probably pretty set in its ways. I think outside of like Elastic, like CrowdStrike or MDE, certain ones aren't going to, I don't imagine, add too many new telemetry sources that are going to matter. If they do, they've done pants anyway. But the 4 for userland we have are userland hooks, DLL notifications, AMS and ETW. You can mess with them, and my issue with like a lot of the monolithic loaders is they will do all of these just all the time. But if you're on MD, right, like what's the point doing the userland hooks? What's the point doing, I don't know, AMS if you're not using any script-based components in your XE? It makes no sense. So the takeaway here is only do the things you need to do. Like, don't do it all the time. It hurts my head every time I see it. Come on, to let things look over. When we get to like runtime, there's some other ones: memory scanners, sleep masking, call stacks. Memory scanners, very aggressive from, again, Sentinel-1. The theme with those guys is they hammer everything in memory. So if you do a lot of memory tradecraft, then maybe, pay special attention when it's S1. And quite the common thing with memory scanners is periodic scans is one, but it's also going to be when certain actions happen. Some EDRs we've seen will do it on thread start, so they'll scan the page address. I think that's Elastic. And then some other ones will do it when memory is been written, not allocated, when it's been written to, and they'll scan it there. So a mental exercise, if you know an EDR is going to scan your memory when it's written, how do you avoid that detection? Call stack analysis is another one. We know Elastic do it. They blog about it all the time. But I've never heard of anyone say, oh man, I was caught by a call stack analysis. I've never heard of it. So again, I think keep it in a repertoire. Be aware of the technique. And I guess just be ready to be able to flick it on if you ever need to. But things like call stack and sleep masking, they're very much, I'm at the C2 level. So I think I said it earlier. If you have the privilege to be able to work with, the source code of a C2, you have your own in-house one. You get that really powerful control over those two things. So if you have a research team or you want a hobby project that will help you on your jobs, build one and just be ready for the instability that will come with that. Again, sleep masking, I'm pretty sure CrowdStrike does that now. I know Fortra are here, so they might tell you. I'm pretty sure they do in their kit. So that's the runtime and memory stuff. We go on to kernel platform. This gets a little bit trickier. If you have the capability to do kernel level stuff, you can just turn all this stuff off if you have something in the kernel. But the things we're going to look at here are kernel callbacks, mini filters, ETW, TI, and then the WSP. So kernel callbacks, I probably wouldn't be too fussed about any of them. I wouldn't actively panic about any of these, because at the point you are entering the environment, you're not going to have any access to handle any of this. Kernel callbacks, process thread image, things like that. That's just going to happen. It's kind of like a post-X thing, I'd probably say, for this stuff. You can just turn all these things off. And if you have access to an EDR to do debugging, you can use things like, I think it's telemetry source, for example, that you see all the kind of that from a GUI perspective. But as I say, this one is far harder to do. I'd just be aware that these things happen. So if you use new process, for example, one of the most common things for a long time back in that 2020 period was, what's it called? Spawn new process, inject to it, that kind of thing. Parent PID, spoofing, that kind of stuff. So again, you're going to create the thread, you're going to inject into it, so you get this long list of OCs. So every primitive you choose is going to have its costs. But yeah, let's not worry about this one. Okay, so at this point we have, can we run here? Is this the right environment? What is the file going to look like? And then we've decided kind of what telemetry we're going to kind of mess with. As I say, I'm not going to give out kind of code for like breaking the certain telemetries. I'm kind of trying to be more abstract than that. So if you know you need a certain one, just go find it. It's like there's a lot of open source research from that stuff now. So we're going to move into stage delivery. There are a bunch of ways to do this, right? So you can shove your shellcode, your exe, your DLL inside the binary itself. I'd say it's a brave move. But in some scenarios, you have to. If you don't have the access to pull it over, then I guess you have to. But for the most part, you probably do. If you're doing like SMB pivots through some sort of environment that has no outbound, but your initial one does, then just do it over UNC, right? Like it's not hard to kind of find these scenarios. The most common one is going to be HTTPS though, especially for initial access. In our scenario though, we have VDI. We could copy over like a local file. So for example, we have a prize at Preempt, which is Bluffy. And what Bluffy does is it takes shellcode and things like that, encrypts it, but then it turns it into like a CSS file or an SVG. And like the numerical values of, the bytes in the shellcode get converted to like, RGB colors, for example. And then we just regex it out after the fact. Stuff like that. Steganography, which is a pretty common one. Works really well as well, steganography. So you could do that. And I probably can, I think I'd probably prefer local file for the scenario we're talking about. You'll see detection from CrowdStrike in particular. New files spawned immediately calls outbound, is a known detection from CrowdStrike. There's a few though. Embedded, which I say. UNC, local file, all sorts. So this is going to come down to your preferred mechanism here and the kind of scenario you're in. As I say, if it's SMB pivots, then UNC or local file could work really well. That's the next thing. Deciding how you want to get your next stage, your shellcode, your C2, or whatever you're trying to do, into this environment. Get something like that. So you'd have your, are we okay to work here? Get the next stage, that kind of vibe. But the next thing is kind of protecting that. Alluded to it a little bit with the Bluffy stuff. But we get these kind of groups. Is it cut off too much? Yeah, it's cut off a bit. So there are 4-ish categories. So we have your encryption, your encoding, your obfuscation, your masking, hiding. I'd honestly probably say do them all. Probably encrypt, encode, and hide being the main ones. As you're not manually, right, undoing these steps, right? It's going to be done programmatically, so it doesn't matter. So if you can have some sort of tooling that just does this step, builds this step for you, kind of as you need it, and then fine, who cares? You can do these about 20 times each. You could take those 3, loop it 30 times and have it work. It doesn't matter, you're not doing it. But this is the main goal here, is to take that stage and protect it. Again, you can tie it back to keying as well, which is another thing I'd recommend. So you can derive some sort of key from some sort of keyed information. Say it's the host name. You could take that host name and then hash it in a different mechanism to what you'd use for keying, and then use that as a key, for example. Stuff like that. Again, just like keying, it's kind of a creativity boundary at this point. And I will say, we've seen teams have their AES kind of reversed because they've left kind of keys in there as well. And then their shellcode's been popped that way. So if you're going to do it key-based, please protect the keys as well. The trade-offs here, though, are going to be down to entropy and things like that. And the easiest way to battle entropy at this point is to go back to kind of like this, right? It can't be high entropy in the file if it's not in the file or in the environment. And also, if a file is high entropy, but it's an SVG file, who cares? You know what I mean? It's fine. This one. So yeah, remember to consider kind of that. If you're going to do encryption, you've got to remember the decryption logic. There seems to be a trend where I think it's a system function 32 for RC4 in Windows is a cool way to do it. First of all, RC4 is a terrible idea, but it's also a known bad function that I don't think has any other use in Windows as far as I'm aware. So why would you introduce 2 OFCs for the sake of RC4? Encoding obfuscation, that's down to creativity. That can, in some instances, lower the entropy as well, but we're getting a bit too in the weeds of kind of entropy and that kind of stuff right now. But the main idea here is protect it. Don't let reverse engineers get it. If your client uploads your stuff to a VT, you don't want someone just from Twitter to that's trusted sex binary and here's their internal C2. That would suck for no reason. Protecting the stager. So the next thing is actually loading that. So far we've talked about everything but the thing people think of when we think of loaders. So this gets incredibly granular, right? What's it cut off there? It's cut off, execute is what it says at the end there. So what we're going to presume when we say stage buffer, that's going to be whatever you've done to get this shellcode or whatever into the environment. It's been unpacked, it's unprotected, it's sitting in just a little buffer in this process. It's just hanging out. So presuming you've done all your tampering, you've disabled what you want to disable, you've accepted your risk and wherever you want, you're now going to start that process. So it breaks down to kind of, I'd say 3.5 steps. So you allocate, you write, you protect, and you execute. In some scenarios, you can have allocate and write in the same step. There's some callback functions of or things like thread pooling, stuff like that. You can kind of have multiple steps in some, but if you break it down to its fundamentals, it is just these 4, I think. I don't think I've missed anything. So what you want to do is for each one, this is the thing I really like, is being able to hot swap each of these steps. So if you know your allocation and write methods by combination, or you have a single function because it works for one EDR but not the other, write it down, remember it, do it again. But if you have a monolithic one that has 4 functions that allocate memory, that's a ball ache of a rewrite, and it's going to take you a lot of time. It's going to slow you down and things like that. So you need to kind of ask yourself, should I run? How do I prepare it? Am I going to do any tampering? Where does the stage come from? How do I protect it? Then this section is how do I turn bytes into something we can actually execute right through to the end. The important thing here is not the individual primitive. It's kind of the decision point you make along the way with it. So every loader, regardless of its sophistication, they don't answer the same kind of questions. So with our XCs, for example, that we're talking about, if we say we're on CrowdStrike Threat Locker, the way we're going to approach that and the decision we've made to double click in this file has been substantial, right? We've thought about everything along the way. So it gives us the best odds of not burning that kind of operation. And if we break it down, you get these kind of options. Oh, that's annoying. So for allocate, there's a bunch of different ways you can do it. Virtual alloc, section mapping, you can reuse existing regions. You can get quite destructive with it if you really want. But if you have done a lot of research, you know this biome you're injecting into, you can break certain functionality of it to get your loader going, then by all means do it. Maybe you can even neuter it as well. what you need to consider for that though is the allocation telemetry, kind of how that memory is going to lay out. So if you're doing virtual alloc, and that's going to allocate private memory, it's kind of rare for that to then, turn executable, unless you're working with .NET and kind of JIT and things like that. With write, it's going to be the visibility of it. This one's, you're getting a bit in the weeds. This way you start entering all those really weird phantom loadery things like hash has worked on over the years. I forget what they're called. But memcopy, map sections, shared views, things like that. Again, each jar is going to handle each of these differently. So again, if you can lab it, by all means lab it. But otherwise, it's probably going to be a case of sticking to something safe, like memcopy. I feel like map sections and shared views are just inherently treated as IOCs now, unless the file you are using actually uses them. It gets a bit weird there. Protection, this one just is what it is. Virtual protect, native APIs, and you can kind of have pre-protected mappings and things like that. But this is your turning the section from writable into something you can execute. Virtual protect, you can do all sorts of different ways there. I've never seen, personally, a detection flip there. It's either about write or execute. I'm happy to be proven wrong there. Execute has an insane amount of options though. So create thread, callbacks, APCs, thread pools. You can just use DLL main. You can hijack an existing thread. You can change the address of entry on a different DLLs, all sorts of random stuff you can do there. But they are going to have all their own telemetry to them, right? And it's kind of hard to talk about that because depending on which one you want to go for, there's going to be different considerations. But my main thing would just be, does it fit naturally into what this process is doing? Which is kind of hard to think about. Things like APCs, getting a bit into kind of the detection by YAML kind of situation. So this one's hard to talk about, but just be aware there's a lot of options, ton of options, and it's going to have to just come down to your familiarity with it, I guess. But thread creation, execute context, and things like cool stuff. The final thing, I've mentioned it a lot, but the post load and kind of C2 internals perspective, there's kind of three other things. Sleep obfuscation and call stacks kind of fall into the same thing, and that's kind of when your shellcode isn't doing, you're not using it, you're not running any C2 commands, it's just hanging out, it's sleeping. How does that look? There's been a lot of research over the years. I mean, that was another gap that came before call stacks, was a ton of sleep obfuscation. A lot of it from Spider and kind of the Echo projects and Gargoyle from Austin Hudson and stuff like that. That stuff's cool. I believe it is in Cobol. But the idea here is just to, when your process is sleeping, just don't have those memory regions that are kind of unbacked, just hanging out. One thing I actually haven't mentioned is kind of unbacked memory, but I speak about that quite a lot in the Tristep blog. But the idea there is when Windows is loading like a DLL, it's going to do something. It is going to be a mapped region. It's going to back to a DLL on disk. And there are some funky stuff you can do with like packaging that up. And if you're going for what I spoke about, like bring in a local file that has the stager in it, you could also bring in extra functionality to kind of handle that process as well. And then the final one is cleanup. Another common thing we've seen reverse engineers detect people on is they've allocated their shellcode and they've got their thread running, but the initial buffer has the shellcode hanging out in it and it's high entropy, and that gets picked up by memory scanners as well. So if we zoom all the way back out, the fundamental problem here, am I doing for time? I've got a few minutes. The fundamental problem is that each component to the loader has to be formalized into, it shouldn't be formalized into one kind of branded loader, like the TS loader, the project loader. Like embedding all this stuff is going to lead you into a lot of rewrites. So what we're going to do is flip based on intent and target. So if you were to abstract it out just way back, you'll get something that looks like this. So you'd have the target environment and the EDR security controls leading to the load decisions. From an outbound perspective, if you're happy and talk to your client about these things, you can just ask them if, what EDR protections they have. Some will tell you, some will play the, haha, you're the hacker card, which is whatever. Some verbose admins will put it in LinkedIn, stuff like that. But for the most part, I just presume you can't find it. And if you do get the information to kind of do that, then perfect, right? All that is going to define your load of decisions. So as I say, if you have CrowdStrike Threat Locker, you can treat that differently to Sentinel-1 and some random app locker you've never heard of. So keeping atomic notes almost on each of these things is kind of what I suggest. And then from there, you can break it down. You could probably go more granular than I have here, but runtime prep, telemetry, interactions, stage delivery, protecting, and then the actual loading itself. You can see like the glory of loaders on Twitter is focused on that bottom step, but everything above that is far more important than the mechanism itself. You'll quite often see people, they even get to this step and they'll get detected, somewhere up that chain. So you need to consider all that too. So the monolithic loader has a few issues. As I said, the fixed execution path, the one environment assumption, you rewrite on failure. It's really hard to maintain. Especially if you start cramming in different mechanisms of different things, and you start having to write abstraction functions to do all this stuff. It becomes a nightmare. And the most common issue they will face is just that lack of modularity. So when it comes to each step in this flow, being able to hot swap each component. So when I say that, I'm talking granular. I'm talking about hot swap, how the allocation works, how the write works, how the call stack stuff works, how you're doing your obfuscation, how many rounds of obfuscation, how many times you encrypt it, all that. I mean, you have like Claude Code, right? You can build like a framework to generate this stuff super easily. And you'll get a lot more longevity out of it. We've never really had monolithic loaders, but we've had ones that aren't as granular, and we'd get into this cycle of we'd be fine for 6 months, we'd have one bad engagement, and then we'd have to go through weeks of R&D to get back to where we were. It was just such a waste of our researchers' guys' time. But taking the more modular approach gets you more longevity. And obviously, the less rewriting the research team has to do, the more time they can spend elsewhere, and the happier the companies overall, right? And because we're so kind of proactive with that research, we can change one component of this without having to change the entire flow. If you find a new way of doing thread creation tomorrow, how easy is it for you to kind of swap that in? And what I'm going to end on is telemetry budget. And what that's going to come down to is something like this. So it's kind of what are you willing to allow an EDR or an environment to see in order to get your loader going. You can't patch everything. You can't stop everything from seeing you. I mean, in the kernel, you probably can. But what we're talking about, you can't, right? So you need to think about what we're willing to let the EDR see. The mistake is thinking that evasion just means you're kind of disappearing. It's not that. For your evasion, you have a cost of other IOCs. So how much is that allocation method worth to you? Like, to get the allocation to work, you have to disable all this other functionality of the EDR. Like, is it worth it for you? Or is it just this other thing? And that's the core idea. It's being able to understand kind of how much it's going to cost you to have that kind of evasion step in your workflow. I'm just going to rush through this last slide here. So, to conclude, I would suggest avoiding monolithic loaders if you have one at the start of the rewrite. Invest in a versatile modular framework instead. So, even if you have a monolithic loader and that's kind of what your company is using for your red teams and it works really well, just split it out into its modular components now. Get the framework working now, so that when it comes time to change how you do it, change how you do a particular step, it's like one Python flag, right? And if a new Twitter loader dropped yesterday, don't write on your red team tomorrow, because I will probably upload it. And then just track what you generate as you kind of go. This is something that works really well for us. Every time you generate a payload, keep it, track it. I know that's going to have a bit of a business cost with kind of storage and kind of that kind of thing. But we track it, we track all the data for it, the commands we use to generate it, all that stuff, and we kind of have to learn from it. And everything I spoke about today is roughly in that list. If you want to read more on any of that, there's honestly a ton more, but that's kind of a realness. Thank you.